Hello everybody, welcome to this video, which is now the 8th in the series, looking at the NACA 0009 airfoil for application to the front wing of a STEM racing competition car. The last video we finished off with an attempt to verify or validate even our solution to our solver. We looked at a couple of academic publications and compared the output of our solver with the data therein. To do that, we referred back to this design table, and in the last video I created another output parameter, the L over D, which we don't have comparable data for, but again it is a metric of interest. But and what I did do in the last video is I said I was going to move straight on into the mesh independence. I'm going to skip the mesh independence on this one here, and what I'm going to do is I'm going to do a little bit more development on the table here, the table of design points. Output a few more parameters to just give everybody maybe a better idea on how it's done and the usefulness of it. And what that will do then, it will hopefully make the process of the mesh independence study somewhat handier. So if I jump back into the project, actually what I'm going to do in the parameter set, because I kind of have a slight idea of what I want to do, and I know I'm going to have to put a specific provision in place for that. I'm just going to take a screenshot here of them values, and I'm going to paste them into Word here just for now, or not Word, until into OneNote. So I just want to keep a record. I'm going to delete off the lift coefficient and the drag coefficient here. Might sound like a bad idea, but by the way, I ran all the design points, the one design point to add again. That's why these are checked off now after my last video. And I come on into solution, and it's going to open up the Fluent solver window again. So if you click setup, it usually says you should be clicking solution. But you land in at the same place. So this is what I'm going to do in this now. I'm going to try to parameterize this somewhat more, that I have less of a requirement to come in and out of these applications, Fluent and meshing and whatnot. So I'm going to do that by taking a lot of the variables that I would tend to adjust in these applications and putting them directly out onto the project schematic in the workbench, specifically onto the parameter table. So what I want to do here is I'm going to take out, I'm going to go down here to parameters and optimizations, my parameters, my output parameter, and I'm going to delete out of here my drag coefficient. I'm going to right click that and delete and confirm that that's away. And then L over D is going to make little sense. I'm going to delete that. And lift coefficient, I'm going to delete that. So why did I go to the bother making all them? Well, it's standard enough to have drag coefficient and lift coefficient, and it helps to corroborate our results. I'm going to put lift coefficient and drag coefficient back in, but I'm not going to put them in a report definition, you see, and explain to you now why in a second. And that go away, delete. Let's go away, lift coefficient. Delete, is it telling you you really want to delete that? I do. Cannot delete convergence reports. Right, so we still have reports now still coming out of these. I'll tell you what I'm going to do. I took them out as output parameters. I'll just leave them there as a second. I don't want them coming out in my workbench. See, my parameters are now gone. I have no parameters left. And that's all right, but I'm about to put them back in. So here's the idea. In the likes of the data here, I have different angles of attack: 0 degrees, 2 degrees, 3 degrees, 5 degrees, and it might very well be that in my evaluation of my car, I might want to look at different angles of attack. So how do we change the angle of attack? I did draw on this, I think, in an earlier video. We don't turn the geometry, because if you turn the geometry, then you have to redo your mesh again. So what we do, we keep the geometry the same, and in our Fluent solver here, we look at our inlet condition in the boundary, in our inlet, and I hit edit. And this was what all this news was about. The magnitude and the direction of the velocity was fully in the x direction. So like if I wanted to put a the velocity coming in at the same magnitude but coming in at or put the airfoil maybe at 10 degree angle of attack, what I could do is I could change the component of the velocity, the x velocity, to have that as coming in at the cosine of 10 degrees, say for instance. So what we're doing, if we have the straight airfoil and the air coming in one to one, it's coming straight in, but we might want to bring it in. Well, go this way here for racing cars, but if we're flying planes, it might come this way. But what I'm going to do here is, as opposed to the airfoil tilting, I'll tilt the flow. Once there is an angle relative to each other, an angle of the air coming in relative to the angle of the airfoil, then I'm fine. So this is what I'm going to do. I'm going to go into a named expression. I'm going to create another new named expression here. This one here I'm going to call AOA, angle of attack. Definition on this one here, this is going to be a constant value and put it in a 0. But what I'm going to do is I'm going to specify this as a DEG in a square bracket to let, it must be a small d, I think, DEG. Yeah, it looks all right. So angle of attack 0 degrees is a constant, but I'm specifying it to have a unit because when I take a trigonometric function of this ANSYS, it will likely take the radian value. So 0 degrees, if I just leave that as a 0 and I take a cosine of a 0, it'll think it's 0 radians. So if I have a 10 degrees, I'm looking for the cosine of 10 degrees. And I just left it as a 10 for an angle of attack, and it costs 10. It'll take that maybe as 10 radians. So I'll specify that as a degree, and now when I take the cosine of the sine of the angle of attack, it will know that it's a degree quantity. So plot, let's just make sure everything's 100%, 0 rads is fine. And I'm going to specify that as an input parameter. So out in my table now, I can choose what angle of attack that I want to go with. Okay, that's in there. I'm going to create another one. And this one I'm going to go for, say, inlet velocity. So go for VEL underscore inlet. And this one, similarly, I'm going to just start off with 29, but in, again, a square bracket. I want to put that in as a unit. So if it has units, put units in it, because when we use these in functions, or we might use them in larger expressions, the likes of which we will be doing our lift and our drag coefficients, we'll write the expressions for them. We want to make sure that our units on numerators match units on denominators so that we have the proper unit for the quantity there that we're calculating. Let's refresh that. 29 meters per second is good. Tell you what I want to do. I want to make that a manage velocity inlet, edit that. I want to make that an input parameter as well. So then I could specify that outside of the Fluent application. Right, let's go for another one. Right, so for this one here, what I'm going to do is I'm going to do the cosine, cos of angle of attack, cos AOA, right, and of course that's going to be the cosine, open bracket, it's a function, AOA. Let's refresh the value. That's 1 because it recognizes the angle of attack is 0, so the cosine of that of 0 is indeed 1. I'm not going to put that as an input parameter because I'm just going to run this calculation in the background, and I don't need it as an output parameter because I really don't need to know what the cosine of the angle of attack is at any one time. This will be used I'll be feeding this into expressions that will be giving me measurements of interest. Okay, that's that one. Let's go for another one, and let's look at the sine of the angle of attack. Sine of AOA. Put an underscore after sine. So this is the name. It's not the expression. Name. This is the expression. Go for sine of AOA in there. Right, and this should come out to be 0, and it does. Current value 0 as a sine of 0 degrees is 0. Again, not an input or an output. don't really need to know, and I'm not going to be putting this in. Right, that's lovely. Now I'm going to be coming in, I'll be doing a couple more in here now in a second, but what I'm going to do is I'm going to just close that off, and I'm going to show you why I took out the lift and the drag coefficients here. So if I go back into my inlet condition, I edit this, right? See where I have to come in to change my velocity here, 29. Well, I'm going to change that, and what I'm going to do is I'm going to select a parameter, because I wrote the expression 29 square bracket meter per second. I specified that as an input parameter. So there it is, velocity inlet, right? So that's going to read whatever the value has been put in for velocity inlet, and that value will be put in now way out here. Velocity inlet, now that's in millimeters per second, that's why that's at 29,000. That's 29 meters per second, so I can change that there, whatever I want, without going into Fluent, without going into the boundary conditions, and open up the inlet, or edit in the inlet parameters. Yep. So similarly, the X component, the flow direction, right? If I want to change the angle of attack on this, I would have to work out what the X component and the Y component is. But the flow direction coming in this road here is going to be the cosine of that, right? So what we can look at is, there it is, the cosine of the angle of attack is going to be the X component of the flow direction. So at the minute, the angle of attack is 0. The cosine of that is 1, so that would be 1. This is now showing 0, and similar to that, the Y component is going to be the sine of the angle of attack. Okay, and apply. So that's done, and that will have an identical same result as what we had before. But out here, what I can now do is specify my angle of attack. Right? This is asking for it in radians now, mind you, see. However, when I put this in, we can broadly ignore that because I've overwritten that in the named expression with the square bracket DEG to specify it as a degree. I'm going to see if I can check to change that there, because that could get annoying, which I do believe I can. If you just bear with me, if I go to view and look at what's the properties? No, it's not properties. I can't mind which toolbar it is. Outline. Yeah, this is the one here. Radian. No, I thought it might let me change it there. But I'll have a wee look onto that one. I'm just going to pull that down out of the road here a wee bit. Let me just get that up. Right. Don't generally have the outline one here up, but look, you can add in your parameters there and write the expressions there as well, as opposed to doing in the named expressions within the Fluent environment. Now, here's the thing. With the velocity and the boundary condition, I was able to write in the X component and the Y component. Now, when we calculate the drag force and the lift force, if you can recall in the report definitions, we needed to also write this is drag. This would have to be the cosine of the angle of attack. This is the sine of the angle of attack. Now, I can't write anything else, only a numerical value in there, so that's a problem. So if I did change my angle of attack and I wanted to calculate a new set of variables, whether it be drag, whether it be lift, whether it be coefficients of friction and this and that, not only would I be changing at a different angle of attack, not only would I be changing the components of the X and the Y in the boundary condition for the inlet, which I've done already, I'd also have to come in here and change it. At the minute, I cannot change it with the named expression that I just wrote, which, it just completely takes away any sort of advantage of writing that. Right? If I have to come in and type this in as like 0.8 or whatever, and whatever the other one might be there, 0.35 or something, I may as well just go into the velocity and do it there as well. If I have to come in, I have to come in. I'm trying to set up a case here where I don't have to come into it, right? So that's why I want to delete them out. I don't want to use a report definition anymore. I have it. It's not an output parameter anymore, but because it's published into a report, which I'm going to have to get rid of the reports here as well. Report definition. So you can just let me away now. Delete that. Yeah, it just won't let me do it. Cannot delete the report is used as far as convergence reports. right. Right, okay. Let me just see if I go into my, that's probably why. I need to take it out of there. Apologies. There they are, convergence and lift. Let's get them out of here first. Delete and delete. Now, because I'm not, it's not feeding anywhere else. Yeah, going ahead. I don't want to look at these again because I could see lift and drag coefficients that'll give me different values now. Right? So this is what I'm going to do. I'm going to write out the expression for lift force and drag force and lift coefficient and drag coefficient myself. I'm not going to use it through the report definition thing because I don't have the flexibility of writing in the vectors there or the components of the velocity vector. So this is what I'm going to do. I'm going to go into report definitions. I'm going to put in a new force report, but I'm going to go down to this pure force here, right? And I'll call this force. I don't know, force full X or something. This is just going to be the full X force coming in, right? Force vector. Everything along this is not specified as a drag force. It's not specified as anything else. I don't want to create a report file. Don't want to create any of that. Don't need it. I just want to know what the force is because I'm going to use this in a named expression. Give that to me in the wall. So this is in the X direction. Force all in X, right, against the wall. Okay. That's all it is now. I'm going to create another one now. Report definitions, new force report, this full force, and this one, keeping it more or less the same. I'm going to call this force full in the Y direction, right, along the wall, but don't care about 0. Don't tell me anything about X. Tell me everything about Y is 1. Okay. Lift coefficient, don't care. Report files. No, don't need that. Don't need that. I'm not printing the console, not creating out reports, nothing like that. Right? And okay. So now I have 2 of these in here. So this is a way, as opposed to writing a named expression that would ask to find force and specifying the wall as a location. The report definition is phenomenal in its own right to do that. What I'm also going to do when I'm at the report definition, and just to help me with my mesh independent study later, is I'm going to put in another monitor here, something that I just want to keep a check on, and that there is going to be in a surface report. I'm going to go for a facet maximum, and here I'm going to go for a Y plus max. My maximum Y plus value is what I want to know about. I'm going to create that as an output parameter because I want to read about that. Report files and report plot, nah, it's just taking up stuff I don't need. I just want to know what it is, right? Y plus max. So what is it? The facet maximum. Look at turbulence, and I'm looking specifically at the Y plus value, right? And on the wall. Okay. There we are, Y plus. So now I'll be able to read that out of my table as well. Now back into my, and by the way, this is what I'm going to be also doing on this. In my reference values here, every time we walk out the convergent, this one could be a problem. Yeah, yeah, see this here? All these reference values. Area 0.025, my reference density, my depth, my length, pressure, temperature, velocity, and all that. All of this here goes in towards the drag and lift forces and coefficients, calculating them report definitions. I can't write in val in that. That won't let me put in anything either. So that's another place I have trouble with. Okay, so I want to get around all of that, and the way I'm going to get around to get that all again is with these named expressions. And I'm going to write one here now for drag force. So the drag force at any angle of attack in general. Let's go for new. Let's go for this as force underscore drag. So how do you calculate the force drag, or force drag, the drag force? Well, the drag force here, if we're going to use this as kind of a an area integrated sum, or an area integral over the surface in the x direction at a cosine angle of attack, plus that force integrated over the full area on the in the y direction by the sine of the angle of attack. If I add the two of them there, I'll have a resolved vector that's given me the drag force, that's coming in against the airfoil. So how are we going to write that? Well, if you recall, in our report definitions, we came up with force full x multiplied by the cosine of my angle of attack plus the force full y multiplied by the sine of my angle of attack. All right. So that there is going to be my drag force. Now I can put that in as a Newton. Newton's not defined. I don't think and small n is not defined either. Maybe it does use like a kilogram meters per second squared or so, but no matter. I'm going to keep it in like that. In fact, because it knows that it's looking at a force here, as was selected in the report definition, it's probably very well aware that I'm dealing with newtons here. All right, refresh value on that. There I'm at 0.2039683 newtons. All right. I'm not going to use force or drag force. I'll put that as an output parameter because I might be interested in looking at that. Okay, and what I'm going to do, I'll just write up another one straight away from that. One named I'm going to double click this to open it up the manager, so it'll be quicker to write in new ones. This next one here, we'll call this force lift. Force lift now is going to be in the opposite way. So yes, again, I'm going to be taking in my force full x, but this time this is being multiplied by the sine of the angle of attack plus the force full y multiplied by the cos of the angle of attack. All right, so this is a perpendicular. It's normal to the drag force. So the drag force, we're going to assume, is going straight at the back of the airfoil. The lift force is going up the other way, right angles to it. So I'm going to put this as an output parameter because I might be curious in seeing how that goes. Okay. So there we go. There's my drag force and there's my lift force. So bearing in mind that you say, how did you get a drag force there without having the coefficient of drag and this and that? Well, you can, because all we're doing is we're just measuring the amount of force that's on the airfoil. The Fluent can calculate that by virtue of the fact there that we have an area, we have a dynamic pressure coming in as well, and we also have our well, I suppose will be static pressures on it, the likes of the normal pressure onto it. So it's calculates out all that. So we'll have that there. Now let's go on ahead and now let's calculate our coefficients. When we have a drag force, all we need to do is divide that by the area, right, which would have been taken from our reference values. So again, in 2D, it's just going to be our chord length, right? A chord length in meters, but don't forget its area, so that's be meters squared, by our density value as well, multiplied by 1/2 our velocity squared. Right, so let's try that. Let's go in here for on that right coefficient underscore drag, and this time I'll put drag coefficient. So this is now, hopefully it's clear why I deleted it in the report definitions, because I'm writing my own one. Right? So this one here is going to be equal to force drag divided by, let's open up a bracket to keep the denominator all the same, 0.5 times my velocity squared, which is, what did I put it in as, maybe inlet? What did I have that in as V? There you are, velocity inlet, capital V, so these are all case sensitive. Velocity squared multiplied by my characteristic length squared. Now, I didn't put my length in as a parameter. I could have done, but I'm always going to be dealing with a 0.025 meter long chord length. So yeah, I could write it in, put it in as variables, store it, look at maybe different chord lengths and all, but I'm probably not going to do it. So for that reason, what I'm going to do is I'm just going to write in 0.025 in here. I'm going to specify that as a meter just to keep my units right. And then I also need to put in density. Right? So I'm going to just write in density because I'm going to assume here the density is going to be the same and go for 1.225. And again, I'm going to specify this as a kilogram per meters raised to the power of 3, close bracket, and close my big bracket. So there's my drag force. Now, there's my drag coefficient. What I would be hoping, if this is correct, that I should be getting out the same drag coefficients that I had before, which is 0.015839 if everything has worked the way it should. So hitting refresh, and there you are, 0.015838741. It's worked phenomenally well. So the denominator on the lift and the drag for the coefficients is the same, so I'm just going to copy that and Control C that. I'm going to use that as an output parameter. I want to look at my drag coefficient. I'm going to hit OK. And then I put in a new, right? And this one, let's put this in as our lift coefficient. Lift underscore and coef. And this one here, as opposed to using the drag force, what I'm going to do is look at force lift divided by that same denominator. Just put in a right there. And again, this one here, comparing what my old lift force was minus 2.9 roughly by 10 to the minus 5, e to the minus 5. That's in that. Refresh it, and there you are, 2.93 e to the power minus 5. So we are spot on. Right, so our functions have worked very well, and now I'm fully independent of having to come into Fluent to work out. I use this as an output parameter. Okay, to come into Fluent to have to change velocities within my my boundary conditions or in my drag and lift definitions. I can specify my angle of attack, and everything should update here by virtue of the fact is that I have very specific expressions written to manage all of that. Right, and I'll close that on up. Right, so that's it. I don't want to do anything now. What I will do in a later video, obviously, is I'm going to be taking that 29 meters per second constant velocity off of the inlet condition, and I'll be putting in a UDF, user defined function, for that, which will track the velocity. It'll have an acceleration term in it there, which will be accelerating me from 0 meter per second starting line up to a final or top speed velocity, and then decelerating hopefully very little into the finish line. So I'll close up Fluent here. I'm going to save these expressions in it. Let's save them. And if I go back into Workbench while that's closing down, you can see how my parameters are now working. This is just closing here in the background. There we go now. So there's my angle of attack. There's my velocity inlet. All these here need to be recalculated again. What I should have did before I closed off Fluent is reduce the amount of iterations that I need to undertake. Let me just do that, please, because I have it up at 1,000, but it's converging much sooner. It's converging there around 300. Having a look at the residual traces. I have taken off the other convergence conditions as well of the drag force and the lift force. I probably should, well, no, I think it should be okay, because when I'm doing the mesh independent study there, I'll be choosing a couple of key variables that I want to look at, and I won't have to use them as convergence, but I should be able to predict if they would converge by the method that I'm going to use, which we'll run through in the next video. Yeah, so let me see run calculations at 1,000 iterations. I'm going to drop that on down to 300. Seem to be more than adequate, right? And now I'll just X that out as well. Reporting interval, I don't mean to go out that often either. I'll go out as 5s. Yeah. Now, while I'm parameterizing this table, and again in preparation for the mesh independent study, I'm going to make one more change. I'm going to parameterize another couple of, another 4 variables here. There we go. And then there's parameters now. Let's just get another wee look. There we go. 0.29. There's my y plus, my maximum y plus. So in my mesh independence study or my mesh convergence study, I'll be able to make sure that as I change my mesh, that my y plus stays within range. My drag force, my lift force, my drag coefficient, lift coefficient. I have a lot of them key factors. Right? Where does this come in? I'm just going to put in another design point now. See, if I was to even just change angle of attack, I put this in at 10 degrees. Right? I can now just run this design point. And it's going to take 29 seconds, but it'll calculate all new values. And in fact, what I'd be doing is, and go back into Winslow et al. 2%, 3%, 5%. Like really, what I should be able to do is go to say maybe 5% here. Run that, get values for my drag coefficient, my lift coefficient, and whatnot. And if everything is solid, right, what I should be seeing is something indicative of this purple line, or even better again, the purple dots, which is the experimental data that Lutz, I believe, found. Okay, so yeah, we'll try that, but that's not for this video now. We're already up to 32, and we're really just parameterizing here just to show you the capability of that. And it's brilliant. It's what I would tend to do. I'd maybe put this in at 2, maybe make this one here, whatever that was, 3 and 5. Update all design points. Go away, have a cup of tea. If there's plenty of design points, maybe it's late at night, as it is now. Leave it running, and in the morning all this here is calculated out for you, one after the other, and you can just let it do its thing. You don't have to calculate this, go and do another one. You don't have to write a completely separate one here with different physics and different setups in it. Just leave it all in the table. Choose what you want to retain, right? Untick what you don't want to retain. Delete off what you don't want here. So I'm just going to delete that design point. Just take these off for now. Delete design point and delete design point. But I want to put in some more things. Just for my mesh independence, I want to be able to adjust my meshing as well. So in project, I need to jump back into the mesh. All right. So hopefully this doesn't take too long to open. Just keeping an eye on time. I'll pause this here, and when this is opened, I'll come back. Okay, didn't take so long. It was only about 10 seconds there. But nevertheless, there's our mesh that we had. Statistically, I have 504,000 elements. So that is a massively heavy mesh as it is. Even before I started mesh independent study, and I know from checking back the y plus value that I'm at about 0.05 of a y plus, so it's hugely tiny. So what I'm going to do before I parameterize anything is I'm going to reduce my mesh size slightly, just because I want to coarsen it up a bit. Yeah, I might try to coarsen this down to about 200. But into 200,000 nodes of that. But what I will do is I'm going to make sure that for my turbulent model, Fluent Theory Guide, let's try this one here. Just always refer back to these things. You don't do anything, number one, that you don't understand, and don't do anything that you're unsure of. So transition SST, I do know this needs, I think, about 150 elements or so along the airfoil edge to work well, and the Y plus value, obviously the one, we're just going to check. There it is. Well, it's not even 100. And 15, I have a thing here, I'm just going to pull it over a wee bit if I can grip it. Let's get that over to there. Yeah, so based on the sensitivity study, the recommended best practice mesh guidelines are at Y plus of 1, which I'm well below, so I'm going to coarse my mesh a wee bit just as a starting point. And a wall normal expansion ratio that's less than 1.1, right? So I'll just check that out. And 75 to 100 mesh nodes, right? So that's along that wall. And down here, note that if separation-induced transition is present, additional mesh nodes in the streamwise direction are most likely needed for a turbine blade that would translate. So we don't have any real signs from what we've seen in the last video and the analysis of separation. Even though we are predicting that there should be some levels of transition in it at that Reynolds number, it doesn't really appear to be the case so much for the NACA 0009 airfoil. Definitely for the NACA 0012, you would be 100% seeing separation bubbles at 50,000 Reynolds. But yeah, between 75 and 100 seems to be the guideline there. That's not. I have to move this thing back over here. That's not in the space and the sizing we're looking at just now. Get this moved over here a wee bit. That's not there. It's along this other one here. See there? That one there. That's the one that we need between 75 and 100 for. There's moving 75 and 100. At the minute, I have 540 in there. Like, that's huge. Possibly, well, not possibly, definitely too much. So it's recommending, what was it recommending? 75 to 100, 75 to 100 mesh nodes in the streamwise direction. These are the amount of division, 75 to 100. And let's try, let's go, what do you think? Maybe about 84, go 90, try 90. Right? That's massively coarsened. I might go a wee bit heavier than that there. What do we go with? Maybe 120, maybe try with 120. See how we go with that. Now, I'll come back down in a second. Now, down here as well, I have 300 in along here. Probably knock that back. I'm going to try that one down maybe till about 180. Yeah, try it on the 180 and see what my mesh numbers come up with. Out the trailing edge here, I also have that at a 180. So I'm going to check my bias factor. That's at 540 there, and that was a massive bias factor to come in here, and that was only the squish in at the wall. That's at 180. That's at 120, which we moved it back to, and the front face there is about 120. I probably could take that down a wee bit. I'll try that one there, maybe down at about, just take it down to 100. Right, so there's 100 in that one, 120 along that, 180 up the back, and 180 there, right? What we'll do is let's generate that and see what that returns us with respect to how the mesh looks. Doesn't really look great. Kind of ruined a lot of the work that we did do. Let me just check that against the back here, this sort of compression. Yeah, we took out a lot of them nodes here. I got that fairly badly crushed. So let me just check if I could, at 540 there. I think that's really doing us any favors. And bring that down maybe half that there, 270. Let's just regenerate, just to try to get rid of that kind of dark shaping line there. Come down slightly, still not flipping brilliant. So bear with me again. I didn't want to footer too much with the meshing, but I'm gonna. 270. I can up I can reduce the amount of elements on that. That will give me slightly better spacing. I'll try 160 on that, and maybe bring that there down as well till 240. Mesh and generate, and that's just trying to deal with this fairly big transition. It's not really having the immediate effect that I want. This one here coming down as much as it has really killed it a wee bit, and that's going very very badly meshed. So I'm going to bring this back up again till 220. I'm going to reduce this bias factor again slightly, maybe down to 180. Just to tighten it back up here, it's getting a wee bit loose out the back. Alright, so that there now has, yeah, blended a good bit better. We still have a nightmare situation here happening at the front, which isn't too bad cell-wise. It's a wee bit skewy there. I'd rather that has come into kind of in a more sweepy angle onto that. And what that means is that I would maybe just need to focus more of the mesh in here, which might be increasing the bias. Might just do that, which there is no bias there. I might have to put a wee bias on that one, just to get. Maybe I'll leave it as it is, because I could expand hairs, changing this around. But back to the point. I want to in the grid study I'm going to do on this for and the method that I'm going to use, which we'll run through in the next video. I'm going to take a kind of a baseline mesh here, and I'm going to improve the mesh by a given factor, and I'm also going to coarsen the mesh as well. I'm down now at 158 nodes. I'm sorry, I'm going to make one more change. I really do apologize for this. 220, 120, and 100. I'll bring this up a wee bit, bring that back to 120. And this one in here, I might tighten. Let's run that again one more time, get another look. It's not, that's actually worked out all right. I'm up to 165 on that. I'm going to keep it at 165 and try it there at 165. Yeah, so I'm going to create a finer mesh that I'm going to increase the amount of these cells, and a coarser mesh that I'll reduce them, and see how we go on. So how am I going to do that? I don't want to have to come in here and take everybody through this exercise of clicking in here, changing it, blah, 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 blah. So what I'm going to do on this one is I'm going to take a couple of metrics out of this, right? I'm going to click on this white box and make a parameter out of that. Right? So this one here is going to be 180 was the first one, which was kind of the, I call that the 7-liner. Next one, 220. That's the aft meshing. 220 was the aft mesh. Take a note of these because I need to change the name so I can. They'll make sense to me whenever I select what I want to change them by. This one here is the kind of the wall meshing, which is edge size in 3. There's 120. It's the wall mesh, and the edge size in 4. There's 120 of that, and that there is the kind of the leading edge mesh. I did put that. I did turn that on. Apologies. There's that one. And there's that. So there's 4 new parameters I put in. Okay, there's nothing doing the face meshing. I'm also going to click on the mesh here, and I'm going to parameterize the number of elements. Right? So then I could see in my table as I run different design points and I refine my mesh or coarsen or do what I do, I can also see how my elements are coming up against that. And what I also want to do is I will be keeping an eye on the y plus value by virtue of the fact that I created that nameless expression in Fluent. But what I'll also do here is I'll look at quality here. I'll choose a metric. Typically, we could look at orthogonality, aspect ratio, skewness, and so on. Element quality. This is just it's kicking up a fairly good distribution here in what we're looking at. But we'll try to keep an eye here on the standard deviations. I don't tend to use the element quality on it. The aspect ratio, not really something there that I do be looking at. But the orthogonal quality there, in some cases, is what I tend to like. For that, I don't generally choose average when I look to parameterize it. I look for the worst of that metric. So what we'll do on this one, and skewness of course is in there somewhere. There's skewness there. You can look at skewness. Skewness is a good one. And in fact, ANSYS Fluent has a fairly nice graphic. I haven't seen it in a long time there, but I used to use it a wee bit in a couple of papers there that I'd looked at, and it did give kind of the range or the targets or the kind of the place, the levels that you should be shooting with with respect to skewness, and I think one was the orthogonality as opposed to the aspect ratio. But yeah, we'll use that as well, and I'm going to go with this one here with the minimum on that, and that'll parameterize that there as well. Okay, so I'm going to close this up now. Let's close that up. And I'm going to go back to my parameter seller, my parameter table here in Workbench when it eventually comes through. And now when we open this up, we have an awful lot more stuff in here now. There's all my edge size, and there's Y plus, drag force, my lift force, my drag coefficient. There's probably lift coefficient. There's my angle of attack still, my inlet velocity. P8, edge size and number of divisions. P9, edge size and number of divisions. P10, edge size and number of divisions. P11, edge size. There's my 4 edge sizes. So again, that's why I wrote down what the names were here. So I can I can change them. Edge size, number of divisions is a parameter name. Doesn't really make much sense to me, but I know that the 181 will be kind of the surround domain. So I'm going to call this one here far field mesh, far field bias mesh. There's probably no need for underscoring it there. I always have a tendency to underscore instead of leaving spaces, but I leave spaces because all the other standard ones here, edge size, and don't have spaces. Right, the 221 I wrote was the aft mesh. Right, so this here is I'll call it the aft mesh. I'll call it divs. Probably should put divs in that there. Bias mesh. No. Bias mesh divs. Edge size number 3. The first one of them was the wall mesh. Wall mesh divs. And edge size number 4 was the leading edge and the inlet divs, leading edge divs. All right. That's why I left that outline of parameters open so I can change the names, and there we are. So now I have up here my angle of attack, my velocity. This is my far field mesh divisions, my aft mesh divisions, my wall mesh divisions, my leading edge divisions, the Y plus, drag force, lift force, drag coefficient, lift coefficient, and the amount of elements I have is over here as well. Mesh elements, and over here then is going to be my mesh orthogonal quality. So I have an awful lot of elements here. Let's get this just moved on over here. Right. Maybe you could argue too much. Don't need all that. Maybe not. Don't room for notes, but so no one will complain about that. Yeah, so there's my table of design points. So now I can create a new one and I can change all of these parameters here, right click on that and update them. So what I'm going to do just for the news is I'm going to put this in at a, go into Winslow and see what his next angle of attack was 2. There's a notable difference there from 0, and I'm just going to see how this runs, but I'm not going to expect anybody to sit and wait. I'm going to put that in 2 and I'm not going to change anything else. Right, I'm still at 29,000 meters per second, so I'm still at a Reynolds number of 50,000. That's another one I could have did in a named expression, was write the named expression for the Reynolds number, but I never. That's for another one. So what I'll do now, I'm going to update all design points. This is going to start rocking and rolling. It's going to run the solver, when hopefully a much sooner amount of time, after 300 iterations, running on a good few less cells, these will start populating up. So straight away here we can see that we're getting values in for the quantity of our cells in our mesh, 165,000, and that's the minimal orthogonality, or orthogonal quality. But yep, it'll calculate this one. That's all calculated. It'll calculate the one underneath. Then what I'll do is I'll look at my my lift force and my my drag coefficient, my lift coefficient, compared against the published data. No need, but just be interesting. And then for the next video, we'll go on ahead into the mesh independent study. Okay, thanks very much. I hope you enjoyed that somehow, but certainly hope you picked up a couple of tips and maybe a couple of ideas for your own CFD analysis on whatever it is that you're looking at. So thanks again for the time, and see you in the next video.